In this video, we're gonna explain the sp3 hybridization of carbon. Let's go! Alright, you already know from the orbital basics how the electrons are distributed in carbon. Just like this. In the first shell, we have a full spherical s orbital. Similarly, in the second shell, there is another full s orbital. And in addition to that, two dumbbell-shaped p orbitals containing one electron each. Lastly, the third p orbital which isn't occupied yet. Now you might remember from the previous video about orbitals and bonds that covalent bonds only occur if there is just one electron in one orbital. That means for carbon, only the two p orbitals can overlap with orbitals of other atoms and create covalent bonds. According to this, carbon can only make two bonds. But in real life, it is totally different. Let's look at methane bonding. Within methane, the carbon atom has 4 bonds to the hydrogen atoms, not only 2. Oh man, eat my socks! Sounds like a crazy paradox. How can carbon take on 4 bonds if only 2 orbitals can overlap? Carbon's magic trick is hybridization. Hybridization is nothing but an intermixture or a recombination. Just like a mule, mules are hybrids of female donkeys and male horses. But when it comes to orbital hybridization, you don't mix animals but orbitals. Back to the carbon structuring within methane. Here you can see the electron configuration of carbon again. For methane, you put the 2s orbital and the 3 2p orbitals into a blender, meaning a sphere and 3 dumbbells. This hybridization is called sp3 hybridization because one s orbital and 3p orbitals are mixed together. The result is 4, hence called sp3 hybrid orbitals. They look like clubs. Okay, the 4 orbitals are combined and you get 4 lobe-shaped sp3 hybrid orbitals. The lobes arrange themselves tetrahedral within methane. So through the sp3 hybridization, you get a carbon atom with 4 sp3 hybrid orbitals and that are arranged like a pyramid. But for methane, we are missing out on the 4 hands of hydrogen. For hydrogen, the 1s orbital is only occupied by 1 electron. The spherical s orbital is represented by the double dots at the end of the lobe. Looks like this. Now, we can draw a connecting line from the atomic nuclei for all 4 hydrogen atoms with the carbon. We can see the bonds are on the connecting line, thus giving it a tetrahedral shape. So we get 4 sigma bonds in methane. The bonds are rotationally symmetric and freely rotatable. Now let's take a look at the change in the electron configuration. Before we had 2 electrons in the s orbital and 1 electron each in 2 of the 3 p orbitals. Because of the hybridization, 4 identical sp3 hybrid orbitals are created. The energy level of the 3 pi orbitals is lowered by the hybridization and therefore the energy level of the s orbital is increased. You can see that now, the 4 sp3 orbitals have only 1 electron each. With this configuration, the carbon atom in methane can take up to 4 bonds through the sp3 hybridization. The sp3 hybridization is not only for carbon atom in methane, but also with other alkanes. Alkanes are the carbon chains without double bonds, for example, ethane or butane. Let's take a closer look at ethane. Not only are sigma bonds created between the sp3 clubs and the hydrogen spheres, but also between the single C atoms right next to each other. This means all the bonds of alkanes and sigma bonds are therefore freely rotatable. Alright, so during sp3 hybridization, 1s orbital and 3 p orbitals are joined together to create 4 sp3 orbitals. This hybridization makes it possible for carbon to take on 4 bonds. And in turn, because of sp3 hybridization, sigma bonds are created. For example, within methane or other alkanes. See ya!